Hey everybody, it's Dr. Lisa. So what we're going to do in this video is solve problem 8.1 from the textbook. And that problem asks us to represent graphically the speciation, I can spell, the speciation of 4-methyl-2,5-dinitrophenol, that's right here, and 3,4,5-trimethyl-aniline over here. There's also, if you look at the textbook, there's a third chemical that it asks you to work on in this particular problem, but it's very complicated. It's got 3 exchangeable protons, and it's just cruel, so I'm not going to ask you to do that. We're just going to do these 2 chemicals right here. So let's first start with the 4-methyl-2,5-dinitrophenol. Here's the chemical structure. The exchangeable proton is right here. This is the one that can be lost, so it's a phenol, right? So can you lose this proton? This is the only proton on this molecule that can be lost. So this is an acid, right? The 3,4,5-trimethyl-aniline over here, this amine group has a lone pair of electrons on it, and it can gain a proton, so this is a base. So we're going to represent the speciation by calculating the fraction that is in the neutral phase. Fraction in the neutral form. Okay, and so for an acid, the fraction that's in the neutral form is alpha, and that's the equation right here. But for a base, the fraction that's in the neutral form is 1 minus alpha. And so we're just going to calculate alpha, but then use 1 minus alpha to calculate the fraction that's in the neutral form. So we're going to do this by using Hammett constants, right? So the Hammett equation, if we go back to our lecture notes here. Here's our Hammett equation. It says the pKa of the chemical we care about is equal to the pKa of the chemical unsubstituted, where instead of all of these side groups, the nitro groups and the methyl, it just has a hydrogen, minus rho, which is a slope factor, times the sum of the Hammett constants, right? So, first of all, we need to know the pKa of the unsubstituted compound, which in this case is a phenol. So we go to this table from the textbook. It's also in the lecture notes. Here's phenol. The pKa of the unsubstituted compound is 9.90. So we put 9.90 here. The other thing we need to know from this table is, here's phenol, and here's rho. That's the slope term for phenol, is 2.25. Rho 2.25. Okay, and then we need to know our Hammett constants for nitro in the ortho position, right? This is the group we care about, so this position here is ortho, so this is the ortho nitrogen, or excuse me, nitro group. This would be the other ortho position, it's unsubstituted. And then this is meta, so we've got a nitro in the meta position. And then we also have the methyl group, and this is in the para position. It's para to the hydroxide. So methyl, para. So these are the Hammett constants that we need. So we're going to look them up over here. Our nitro group, where's nitro? Here's nitro. In the meta position, it's 0.73. So nitro meta 0.73, and then nitro in the ortho position. Here's nitro in the, oh, wait a minute, we don't have the ortho position. What are we going to do? We need to go to this table, and here's our nitro for phenols in the ortho position. Our value is 1.24. Oops, that's the fully baked cake. Shh, you're not supposed to see that. So in the so nitro in the ortho position, 1.24, and then methyl in the para position. Let's see, here's our methyl substituent in the para position. It's minus 0.16. There you go. So now we need to sum up all of our Hammett constants, right? That's this part right here. So the sum of those Hammett constants, 1.81, multiply that by rho, so pKa of this chemical is the pKa of the unsubstituted compound which is 9.9, minus rho, which is 2.25, times the sum of the Hammett constants, which is here, and our pKa is 5.8275. So now we want to, that's our pKa. Now we want to plot the speciation graphically. So the pH, it's telling us to do it over the pH range 2 to 12. So let's do this in 0.5 units. So 2, 2.5, 3. Once I have done a few of these examples, I can now just click and drag and this will update automatically. We're going to stop here at 12. Okay, so there's our pH, and we're going to calculate alpha. Remember, because alpha is the fraction that's in the neutral form, and here's our equation for alpha. You can ignore all this. We're just going to use this part of the equation. So alpha is equal to 1 divided by 1 plus, remember your parentheses, 10 to the, I'm going to put another parentheses here, oops, parentheses, pH, which is here, minus our pKa, which is there. And of course, this is always going to stay in that cell, so I use my F4 to make the dollar signs appear. And now I can float over here until my cross becomes totally black, double click, and there you go, voila. So now I can plot this, insert, I'm going to insert a dot plot here, and you can see pretty straightforward. If you want, we could format our data series and we could add some lines here, and that would look beautiful. So we want to call this is our 4-methyl 2,5-dinitrophenol in all caps, because I have caps lock on. And I always like to be a little fastidious with my charts, label my axes. So the horizontal axis is the pH, and the vertical axis, axis title, vertical axis, is the alpha. So that's the amount that's in the neutral form. And alpha will never go above 1, right? So I might want to double click on this and go over here to the little axis options thing and say I want my maximum to be 1, because it's not really very realistic for it to go greater than 1. I could also, if I wanted to, I could format these as percents, and then this would update automatically. So here's my speciation of 4-methyl 2,5-dinitrophenol as a function of pH, and this is alpha, which is the percent or amount that's in the neutral phase, that's in the neutral form. So now we can do the same thing for our buddy over here, 3,4,5-trimethyl-aniline. And so again, we want to know the pKa of the unsubstituted form, which is aniline. So we go to our table here. Here's aniline. And so the pKa of the unsubstituted compound is 4.63, and the slope is 2.9. 4.63 and 2.9. 4.63 and 2.9 is our rho value. Then we're going to need, again, to put our Hammett constants in here. And so now we just have 3 methyl groups. Let's get rid of this. We've got, so these are the 2 ortho positions. They are unsubstituted, right? So we got 2 methyl groups in the meta position. So methyl, meta. So what I'll do is I'll just list this twice since we have 2 of them. And then we also have a methyl group here para to the amine group. So we have a methyl para. Methyl para. So we want to look up those Hammett constants. Here's our methyl group. When it's in the meta position, it's minus 0.06. Minus 0.06. And when it's in the para position, methyl group in the para position, minus 0.16. There you go. All right, so just like we did before, we're going to sum those up. And just like we did over here, we're going to calculate the pKa of our compound. We can even just copy the formula over because I've been careful to put all my numbers in the right places, and we can check and make sure. Yep, I've used everything correctly here, so that should be my pKa. Now, but remember that this is a base, right? So what I need to calculate now to plot the fraction that's in the neutral form is to calculate 1 minus alpha. So we're going to kind of do the same thing we did over here. Just going to copy this, put it over here. We already have our formula, except now instead of B25 over here, we're going to be using this pKa. Double click, copy that down. So I went through that really fast because I'm just copying, but again, this is alpha. Now I've calculated alpha using this equation, 1 over 1 plus 10 to the power of pH minus pKa. But what I really want here, because I'm plotting the base, is I want to calculate 1 minus alpha. So we'll call this 1 minus alpha. And to do that, that's easy enough. We'll just put this whole thing in parentheses. And then we'll do 1 minus this. Double click, copy it down. Okay, and then we're just going to do the same kind of thing, and I'm just going to be really lazy here, and I'm just going to Control-C to copy, Control-V to paste, and then I'm going to drag this over here. So now we're plotting 1 minus alpha. So again, and of course now this is no longer, this is now our trimethyl aniline. I don't spell very well, but I think that's right. I don't spell too good, but I'm doing my best. Okay, so again, the point is that this is, in both cases, we're plotting the fraction that is in the neutral form. But because this is an acid, the fraction in the neutral form, most of it is in the neutral form at low pH when there's plenty of protons around to protonate the acid and leave it in its neutral form. And then as the pH gets higher, there's not as many protons around, there's a lot more hydroxide, so the hydroxide pulls off the proton and leaves you with a negatively charged conjugate anion. For the aniline, at low pH, there's plenty of protons around to protonate this amino group. And so it's positively charged. So the amount that's in the neutral form is almost zero. Then as the pH goes up, there's more hydroxide around and less protons. That pulls off the proton that was on this amino group and leaves it just as you see it here in the neutral form. So the fraction in the neutral form goes up to almost 100%. Given the fact that our pKa is 5.44, let's just for fun call it 5.5. So when the pH is about 5.5, the amount that's in the neutral form is about 50%. Remember, we said when the pH is equal to the pKa, you have about 50%. You're 50-50 in the neutral form and in the charged form. And of course, the same thing is true over here. Here, the pKa is about almost 6. So at a pKa or a pH of 6, we're just about 50% in the neutral form. So that's how you use the Hammond constants and how you can graphically show the speciation of these different chemicals. And then we'll move on to the next video where we do some more example problems using acid-base constants.